Hey everyone, Ivan here. Welcome back to our Computer Science Fundamentals series. Today we explore the fascinating bridge between hardware and software, how physical electronic components create the digital experiences we rely on every day. Yesterday we explored bits and bytes, the language of computers. Today we're going a step further to understand how physical components process these bits to create everything from spreadsheets to video games. Think about it. When you tap an icon on your phone or type on your keyboard, you're initiating a complex chain of physical events involving electricity, silicon, and magnetic fields. Yet the end result feels completely virtual. Text appears, videos plays, or games respond. Let's demystify this seemingly magical transformation from the physical to the digital world. At the heart of every computing device is the hardware, the physical components you can touch. X breaks down the essential parts. The central processing unit, or CPU, is often called the brain of the computer. It's a small silicon chip containing billions of tiny transistors, those electronic switches we discussed in our binary video. The CPU's job is to execute instructions, performing calculations, moving data, and controlling other components. Modern CPUs can execute billions of instructions per second, which is why they generate heat and need cooling. Next is random access memory, or RAM. Your computer's short-term memory. Unlike your hard drive, RAM is volatile, meaning it loses its content when the power is turned off. It provides ultra-fast, temporary storage for data the CPU is actively using. For permanent storage, we use storage devices like hard disk drives, HDDs in the past, with spinning magnetic platters or solid-state drives for now. SSDs that use flash memory chips, and then these retain data even when it's powered off. The motherboard connects all these components, providing pathways called buses for data to travel between them. Think of it as the nervous system of the computer. Input devices like keyboards, mice, and touch screens convert your physical actions into electrical signals. Output devices like screens, speakers, and printers convert digital data back into physical form you can see, hear, or touch. For special tasks like rendering 3D graphics, we use dedicated processors like graphics processing units, or GPUs, that excel at performing many calculations simultaneously. To understand how hardware processes information, let's look at the fundamental rhythm of computing the instruction cycle. First, fetch. The CPU retrieves an instruction from memory. Second, decode. The CPU figures out what the instruction means. Third, execute. The CPU performs the operation. Fourth, store. Results are written back to memory. This cycle happens billions of times per second in modern computers. Each instruction might be something simple like add these numbers or move this data from here to here. These instructions are represented in the computer's most basic language, machine code, which is just binary number. For example, the instruction 0100011110 might be add the content of this memory location to the processor's accumulator. Modern CPUs contain multiple processing cores that can execute different instruction cycles simultaneously, dramatically increasing performance. While hardware deals with electrical signals and binary data, humans think in terms of tasks and goals. Software bridges this gap through layers of abstraction. At the lowest levels is machine code, the raw binary instruction that the CPU can directly execute. This is nearly impossible for humans to work with directly. One step up is assembly language, which uses symbolic names instead of binary patterns. For example, ADB instead of 101001111. This is still very hardware specific. Higher level programming languages like Python, JavaScript, or C++ allow programmers to write in more human-readable terms. A single line of these languages might compile to dozens of machine instructions. The operating system like Windows, Mac OS, or Linux provides critical software services that manage hardware resources and provide consistent interfaces for applications, and it handles tasks like managing memory allocation, scheduling which programs get CPU time, controlling access to storage, standardizing input-output operations, and so forth. Finally, application software sits at the top of this stack. The programs you actually interact with, from web browsers to video editors. These applications use services provided by the operating system rather than talking directly to hardware. How does human-readable code become machine instructions? There are two main approaches. In compilation, the entire program is translated into machine code before execution. This creates a fast, executable file specific to a particular processor architecture. Languages like C, C++, and Rust typically use this approach. In interpretation, code is translated line by line during execution. This is more flexible but typically slower. Languages like Python and JavaScript often use this approach, though modern implementations use techniques like just-in-time compilation to improve performance. Some languages like Java and C# take a hybrid approach, compiling to an intermediate form that runs on a virtual machine, which then translates to specific hardware instructions. This provides a balance of performance and platform independence. Computers use hierarchy of storage systems, balancing speed against capacity and cost. At the top are the CPU registers, tiny ultra-fast storage locations within the processor itself. This holds the data currently being processed. Next is the cache, small amounts of very fast memory built into the CPU. Modern processors have multiple levels of cache, L1, L2, L3, with increasing size but decreasing speed. RAM comes next, larger but slightly slower. A modern computer might have 8 to 32 gigabits of RAM, accessible in tens of nanoseconds. For long-term storage, SSDs provide access times in microseconds, thousands of times slower than RAM, but still very fast. While traditional hard drives work in milliseconds, millions of times slower than RAM. Finally, network and cloud storage provide vast capacity but with significant latency measured in milliseconds to seconds. The system automatically moves data between these levels as needed, keeping frequently accessed information in faster storage. This creates the illusion of having both vast storage and rapid access, even though these are physically incompatible properties. From transistors to web browsers, computing systems represent one of humanity's most remarkable achievements, creating virtual worlds from physical components. What makes this particularly amazing is that the fundamental principles haven't changed much since the earliest electronic computers. We've simply made the components smaller, faster, and more energy efficient, while adding layers of software that make them easier to use. Understanding this hardware to software bridge helps you appreciate what's happening beneath the surface of your devices. Every click, type, or voice command initiates countless physical processes that translate your intent into computational action. In the next video, we'll explore algorithms and data structures, the patterns of organization and problem solving that power efficient computing. But for now, I'm curious, which part of the hardware-software relationship do you find most fascinating? Let me know in the comments. And if you like my video, please give me a thumbs up and also consider subscribing. So this is Ivan, keeping you at the most to understand the technologies and shaping our world. Thanks for watching.